Good morning everybody, and great to see such a big audience for this talk today. I'm going to be telling you a bit about the InSAR capability that we've been growing in the geology section for the last 4 years and how we can use that to monitor subsidence of the land. I'll also talk a little bit about the work we've done to develop new geodetic infrastructure to assist us in interpreting this InSAR stuff. So hopefully by the end of this talk you'll be able to understand what these psychedelic colour fringes are all about and how we can use those to look at land subsidence. So as always with these big projects, a lot of people have contributed to the work, and this is the team. I'd like to acknowledge in particular Shane Nankoro and Marty Hazelwood, without whom we would not have been able to deploy the new geodetic network in the Surat Basin on time and within budget. I'd also like to acknowledge my colleague in the InSAR team, Sarah Laurie, who has produced a lot of the material that you'll see in today's talk. So here's a quick overview. I'll give you a bit of background. I'll talk about the geology, the AGOS project and the Surat Basin. I'll then tell you about what is InSAR, and then I'll give you a bit of detail on the InSAR analysis work we've been doing in the Surat Basin. I'll then talk about radar corner reflectors and how we can use this infrastructure to assist us with the InSAR analysis. And then I'll describe the new geodetic network that we've deployed in Queensland. So geodesy is the study of the shape of the Earth and how that shape changes over time. So principally we're looking at deformation of the crust and how that changes over time. Now, Geoscience Australia is responsible for the upkeep of the National Geodetic Reference Frame. And we do that using, amongst other things, a network of 120 continuously operating reference sites around the country. And using these reference sites, we're able to very accurately track the movement of the Australian continent through time. But what I'm showing in the bottom here is the distance between those sites, and maybe you can just about see the distance between the sites tends to be at least around 100 kilometres or more. So if we're actually having deformation processes that are smaller than this length scale, so less than 100 kilometres, it will not be picked up by our reference network and therefore will not be captured by our geodetic datum. So we're doing some work to develop using remote sensing method called InSAR to actually capture smaller scale deformation features and feed those into the geodetic reference frame. Back in 2011, the Australian government funded the Australian Geophysical Observing System, and this was a project to develop new ground infrastructure, new earth science infrastructure to support research into energy-related issues. And Geoscience Australia was responsible for implementing the geospatial components of AGOS, which are shown on this slide. Perhaps the people in this room will be most familiar with the robotic antenna calibration facility, which is actually sited here at GA down at the back of the support building there. Today I'm going to talk about mostly the geodetic network that we deployed as part of AGOS. And that network has been deployed in the southeastern part of Queensland in the Surat Basin. We deployed 65 new geodetic sites across the basin, where the Surat Basin is outlined by this grey polygon. And 40 of those sites highlighted by the yellow points have a co-located radar corner reflector. So I'll come back to this later in the talk, but that's just to set the scene on the AGOS project. But why did we choose to deploy this in the Surat Basin, you might ask? Well, the Surat Basin is a large Jurassic Cretaceous basin that covers the southeastern portion of Queensland and the northern part of New South Wales. And the Australian Gas Resource Assessment done in 2012 by GA and Bree identified this basin as the largest onshore gas reserve in Australia. At that time, there was proved and probable reserves of coal seam gas exceeding 24,000 petajoules. Production of that resource began in 2006, and this graph here, the green line here, the green area shows the increase of that production since 2006. And at the end of last year, 160 petajoules of this coal seam gas resource was being produced per year. Our estimates of the proved and probable reserves of coal seam gas have also increased over time, and now there's over 32,000 petajoules of known coal seam gas in the Surat Basin. So this is a significant energy resource for Australia, and as a result, production is increasing. What I'm showing you here is the expansion of the number of production wells that have been drilled in the Surat Basin over the last 15 years. And particularly since 2006, you can see an explosion in the number. So by the end of last year, there's over 7,000 wells drilled in the Surat Basin region, targeting the coal seam gas reserves. At each of these sites, a well is drilled into the ground to a depth of about between 300 and 800 metres into the Jurassic Walloon coal measures, and water is extracted from this well to reduce the pressure in the coal seam. When enough water has been produced, then gas comes out of its adsorbed state in the units and also comes out to the well. And this is a photo of an example of some of the wellhead infrastructure you see in the Surat Basin. In the Surat Basin, typically you need to draw out large quantities of groundwater, and this means that you're likely to see subsidence at the surface due to the amount of water we're extracting. So, and that subsidence and the patterns of the subsidence should be visible in geodetic techniques. So I'll talk now about one of those geodetic techniques that we're going to use to have a look at subsidence in this region. That's the InSAR method. Before I can tell you about InSAR though, I need to tell you about what is SAR. SAR stands for Synthetic Aperture Radar, and it's a side-looking active imaging radar that is mounted on travelling platforms such as orbiting satellites or aircraft. So if this is our platform, which is travelling in this direction, the radar shines a beam of radar energy down to the ground with a slanted path, and it images the ground of a certain swath width, typically up to about 100 kilometres in width. The clever thing about the synthetic aperture radar is it synthesizes a much larger antenna than it actually is in physicality. So for any particular target on the ground, it's imaged in the radar for a long period of time as that platform travels in space. And if we look at the Doppler echoes of this target as time progresses, we can do some fancy digital processing and pick out targets with very high spatial resolution. So the pixel size in the image is typically up to meter resolution. So the radar operates in the microwave frequency band, and we typically use the X, C and L bands for geoscience applications, and that's microwave wavelengths in the 3 to 24 centimeter range. So the radar measures a complex signal. That means that for each target, we measure the real and imaginary components of the reflected signal. And we can represent that in two ways. We can represent it as the magnitude of the return, otherwise known as the amplitude, and we can look at it in terms of the phase. So here's an example of the amplitude components of the return signal. And what we're looking at here is a time series of TerraSAR X images over the northern suburbs of Canberra in Gungahlin for the last couple of years. So what you can see is the dark regions represent backscatter that's very poor, or relatively poor, and the white areas are backscatter that's very high. So what you can see is there's a correlation between the built environment and high backscatter returns. And for areas like bushland and paddocks, there's a lower backscatter. Some interesting features to point out in this animation are that you can actually track the expansion of some of these suburbs through time. If you look at Crace, Harrison, Bonner, you can see that as these suburbs are expanding, we can detect that in the SAR images themselves. In the bottom left corner here, there's some agricultural activities ongoing, and the backscatter changes through time, presumably due to irrigation changes over time. The dark bodies here represent water bodies. They have the least good backscatter response to SAR imagery. And if you look in this location here, you can see that we can monitor changes in the size of these water bodies through time. This is an example of a dam that's expanding and contracting through time as rainfall changes. We can also see the extension of the Gungahlin Drive the horsepower drive extension as we're going. So there's a lot of little applications we can use this imagery for, but that's not what I'm going to talk to you about today. We actually are more interested in the phase component of the signal, and that's what we use in the InSAR technique. So InSAR stands for Interferometric Synthetic Aperture Radar. So an important point to note here is that this is a particular method that we're using on the SAR data, and that method is interferometry. So it's a repeat pass remote sensing technique where we use 2 or more of these SAR images. And here's an example of the geometry of the acquisition. So the satellite comes by on its first pass. It fires a radar beam to the ground. That is reflected off the ground surface, and some of the energy will return to be measured at the radar satellite. If we come back the second time, perhaps there has been some ground movement, in this case some subsidence due to movement on a tectonic fault. You can see here that the number of wavelengths between the ground and the satellite has increased. So if we compare that change in number of wavelengths in the first image with the second image, there's an actual offset in the phase between those 2 wavelengths. And this change in phase is what we refer to as a range change. So what we're actually measuring is it's a geodetic measure similar to what we might see in surveying practices and range change. If we look at that spatially here, we have the amplitude image and the phase image for the first pass, and the same for the second pass. The images look the same, and the phase image itself looks like random noise essentially, but if we take the 2 phase images and do an interferometric process on it, some magic happens, and you end up with this fringe pattern, which we saw at the beginning. So what we're looking at here now is fringes, where each fringe corresponds to 1 full wavelength of range change between the 2 times of the SAR image. And so whereby the full color scale corresponds to 2 pi radians change of the phase. So using these interferograms, we can actually look at patterns of change between the 2 times of the SAR images. So if we take a profile through that interferogram, the signal would look something like this. The signal is wrapped in a sawtooth pattern between the values of 0 and 2 pi, so 1 full wavelength. But what we're actually interested in is the continuous pattern of deformation in the image. So what we must do is count up the number of these cycles and do that spatially to end up with the continuous signal. And that's the process that we call unwrapping the interferogram. So there's the interferogram when it's wrapped with the fringe pattern. When we unwrap it, we end up with a continuous phase signal over the area. Now you'll notice the color scale here for the wrapped interferograms between 0 and 2 pi, and now we're a continuous scale of radians between 5 and minus 30 radians. This is in the line of sight of the satellite, and I'll explain what that means now. So, as I mentioned, the radar satellite will fire radar at the ground with a slanted path, and that slanted path has an incidence angle that we can measure with respect to the vertical. And if we look a bit closely at the change that's happened at the ground surface here, you can see that the ground has moved with both a vertical component and a horizontal component. But what we actually see with the radar is that both of those components of deformation mapped into the one-dimensional line of sight of the satellite. Now we can decompose that signal into horizontal or vertical if we're interested in any particular aspect of that deformation. So for subsidence, we're primarily interested in the vertical component. And if we can do these operations on the data using the cosine or the sine of the incidence angle to determine the vertical or the horizontal components of that signal. But in today's talk, I'll just be showing you the line of sight deformation, so that's in this direction. Another important concept is that the InSAR gives us a relative signal, and that's because it's a double difference measure. So I've already talked about the difference in time that's recorded in the interferogram, but there's also a difference in space. And this arises because of the unwrapping procedure that we use on the interferogram. So during that unwrapping, we must choose a reference pixel somewhere in the interferogram from which we propagate out the phase values. So that pixel would be 0. And depending on where we choose that reference pixel, the character of the unwrapped interferogram can look quite different. If I draw a profile through those interferograms, though, you can see in this profile that the character of the signal that we see there is very similar, but there's just an offset between those the two profiles. So what we're seeing here is a relative signal. But how can we interpret that in an absolute sense? And that's a good question. We actually need other data, other geodetic data, to be able to validate those signals and represent it in an absolute sense. And this is why we've been investigating using radar corner reflectors and co-located geodetic measurements from other techniques. So GNSS is one of those geodetic techniques, and it has several advantages over interferometric observations, but then again, InSAR observations have their own advantages. So GNSS are point measurements of particular places in the landscape where we deploy instrumentation, but they give us three-dimensional observations of any displacements that occur. InSAR, on the other hand, give us spatially dense observations, but as I mentioned, they're only in the one-dimensional line of sight of the satellite. So can we leverage off both of these geodetic techniques to actually fill in the gaps between our traditional geodetic networks to characterize deformation that's falling between the gaps of those networks? So that's really been the focus of our research. So I'll talk briefly about some of the applications of InSAR. Back in the early 90s, InSAR was first applied to studying earthquakes. And here's an example of an interferogram generated by colleagues in the UK of the Chile earthquake last week. So what we can see here is a lot of fringes, which is implying that there's a lot of ground deformation associated with this earthquake. And in fact, if we count up the number of fringes there's 140 centimeters of movement in the line of sight of the satellite. So this is a very effective technique for studying earthquakes. We can also look at strain accumulation signals that may be occurring on tectonic faults, in particular studying slip rates as strain is accumulated before and after earthquakes are occurring. We can look at volcanoes and how the ground surface is moving due to movement of magma beneath the volcano. And we can use it to monitor subsidence and uplift that may be occurring due to human influences such as groundwater extraction, gas extraction, coal mining, or even carbon capture and storage projects. So here's an example of a study where we were looking at subsidence. We're just south of Sydney here. Sydney's probably up here somewhere. Campbelltown just off the image, and Wollongong to the southeast of the image, and we have the Hume Highway passing through the image here. What we're looking at is the line of sight velocity that we've derived from a stack of interferograms covering about a 4-year period in this region. And what you can see there is there are a few spots where we see pretty high velocities, so up to 15 to 20 millimeters per year. These anomalies are actually associated with longwall coal mining in this region, where coal is being extracted in the subsurface from a seam of about 3 meters thick. And when that coal is extracted, we're actually seeing a subsidence at the surface. We can also look at this data in terms of the history of the displacements through time, using if we use linear inversion techniques to analyze the individual interferograms. And that's what I'm showing here in this animation. So you can use this to accurately determine the spatial patterns of subsidence as they evolve, and also to determine the magnitude of those signals. So for these three anomalies, we're looking at displacements on the order of 80 to 100 millimeters, so quite large displacements associated with that coal mining. If we know something about the source of that deformation, then we can invert the interferograms to work out some physical properties of the crust itself. And in this case, we've been doing some volcano monitoring of the Rabaul caldera in Papua New Guinea. And by inverting interferograms over a period of 4 years in this region, we've been able to identify the volume change that's occurring in the subsurface magma chamber at this volcano. So that's what's shown by the red points in this diagram here. And over a period of about 3 years, we've seen a cumulative volume change in that magma chamber of 20 times 10 to the 6 meters cubed, so quite a big volume change there. Then at the beginning of 2010, something changed in the volcanic system, and that deflation signal that we've seen up until that point changed to inflation. This signal has actually been verified using independent geodetic measurements from GPS networks at the caldera. In particular, in the grey points here, I'm originating from a GPS station here, which is just above the interpreted centre of the magma chamber. And what hopefully you can see is that there's a pretty good agreement between these two independent geodetic data sets for this example. Okay, so that's what InSAR is. Now I'm going to talk a bit about the InSAR analysis we've been doing in the Surat Basin. So we've been concentrating on a region of about 150 by 150 kilometres area that's focused on the Miles and Dalby region. This is just to the east of the main country town of Toowoomba. And this is a region where there's a lot of coal seam gas wells, and production actually started in 2006, as I mentioned earlier. We've been using data from the ALOS pulsar sensor, which is an L-band Japanese sensor that was operational between 2006 and 2011. So we've been doing analysis in two tracks of this data, which I'll refer to as the west and east track. Unfortunately, this talk came probably 2 weeks too early, and I won't be able to show you any of the final results today, but nevertheless, I can show you some of the complex signals that we must deal with when we're doing this sort of InSAR analysis. So for the two tracks, the west and eastern track, we had a total of 22 and 20 images, and from those images we formed interferograms numbering 113 and 95 between those 20 to 22 images. So we form lots of different interferometric combinations between the different interferograms. And that arises with total numbers of observations exceeding 9 or 10 million. So it's a large data set that we're generating here, and we make use of the national computational infrastructure to streamline this process. We've set up the processing in a parallel fashion that makes use of many CPU cores on that machine, and what in real terms takes 60 to 70 hours to process, we can actually process using the NCI in less than a day's period. So this is what one of the unwrapped interferograms looks like for the eastern track. And the only thing you can really see in this interferogram is these signals, which cover a large part of the interferogram and have a magnitude of at least 7 centimetres in the line of sight. These are pretty large signals, and what I'm going to tell you is these aren't deformation, thank God. The interferogram itself is the summation of lots of components, lots of signal components, and deformation is only one of those components. One of the signal components arises from the changes in orbit of the two satellites between the two times of the SAR acquisition. So the satellite never returns to exactly the same point in space. There is a spatial baseline between the two times. And during the processing, we do take that into account using models of the orbit information of the satellite. But the models are only good to a certain degree, and there tends to be a residual signal that will map into the interferogram as a long wavelength signal. So that could be within our interferogram. We also have changes in topography across our imaged area. It's never the case that we have totally flat Earth in our imaged area. So we must take into account the topography, and we do that in our processing chain by subtracting the effect of a digital elevation model. A third component comes from atmospheric changes between the two times of the images, and what last week in Canberra was very good weather, today has turned to be very cold again. So we all know that the atmosphere is quite dynamic. And over the course of the revisit of these satellites, which is at least a week or maybe up to a month, you're never going to have the same atmospheric conditions between the two image times. So the radar signal itself is attenuated by water vapour that may be present in the atmosphere. So if on the first pass we don't have any water vapour, on the second pass we do, we're passing through a big cloud system, that water vapour will act to delay the phase signal that's coming back, and that will map into the interferogram. So these signal components add together to mask the deformation signal of interest, and we must do some clever processing tricks to try and remove those. In the Surat Basin, a lot of agricultural activity is ongoing as well. You can see through this interferogram there's some very small scale fluctuations in the phase, which actually align very closely to paddock boundaries. And the community has for a long time not really known what the cause of these signals are. And initial thought was that it's due to actual physical deformation due to soil swelling in the paddocks themselves. But could it also be that there's penetration differences of the radar signal into the soil surface? Changes in the growth of crops in these paddocks that's introducing scattering changes that manifest as phase delay signals. Or what people are more recently thinking is that it's actually due to electrical changes in the soil itself. So if there's been rainfall between the times, then the soil becomes more or less saturated, and that affects the electrical properties that the radar sees. So nevertheless, these introduce complex small-scale signals that we must deal with if we're to find the signals that we're looking for. Another concept that I'm going to explain is of the interferometric coherence. What that is a measure of the phase similarity between the two SAR images. So, or you might think of it as a phase quality. So if you have good coherence, the phase is very good quality and you can be confident in what you see in the interferogram. However, if you have poor coherence, it's much more noisy and you can't interpret it as easily. This is a map of the interferometric coherence for one interferogram, and it varies between a coherence of 0 and 1. So 0 is very poor coherence and 1 is very, very good coherence. And if we, you can see as we increase the time span of the interferogram, the overall coherence is degrading. So this can introduce noise signals into interferogram that we must deal with. But if we look at a stack of the average coherence for all the interferograms on this eastern track, you can hopefully see a good correlation between an optical image. So the red colours here are where we see very good coherence, and that's matching where we see forested region. And the blue area is very much relatively poorer coherence, and that correlates nicely with where there's agricultural activity ongoing. So these byproducts of the interferometric processing could be useful for mapping land cover and temporal changes in land cover. So once we've dealt with all these signals, the noise signals in the data, what was looking like this ends up looking like this. And we've reduced the range of the phase that we see in the interferogram from what was 7 centimeters in this interferogram to only about 25 centimeters. Nevertheless, we do still need to validate the signals that we're seeing if we're going to interpret them as deformation. So I'll move on now to talk about radar corner reflectors, which we use for that validation. A radar corner reflector is a device that we deploy in our area of interest. It's a passive device that reflects incoming radar energy, and that reflection is very bright and consistent through time. So it's constructed of 3 orthogonal plates. The radar energy comes in, bounces off the 3 plates, and is sent back in the same direction as it came in. So somewhat similar to an optical prism. In terms of the phase, the corner reflector acts as a persistent scatterer, so that we can get very high signal-to-noise ratios of ground displacement through time. So here's a simple example of that. If this is 1 pixel, that pixel is comprised of a number of distributed scatterers that contribute to that signal. If we do a simulation of how that might change through time, the phase response varies almost randomly between the plus or minus pi interval. However, in the example below, we've got a much brighter scatterer, maybe a corner reflector, introduced into that pixel. And that bright scatterer acts to focus the phase and give a much higher signal-to-noise ratio. And if we look at the brightness of that target that we introduced into the pixel, the brightness itself corresponds to the standard deviation of the phase that we observe, so i.e. the width of this zone of focusing. So the brightness can actually more accurately determine the radar cross-section of the target, and that theoretically can be given by this simple relationship. So the radar cross-section is proportional to the dimension of our corner reflector to the power 4 and inversely proportional to the wavelength of the radar squared. So that's what I'm plotting in this graph. We've got the size of the corner reflector on this axis and the response, the RCS, the radar cross-section on this axis. And as you can see, if we increase the size of the reflector, we're increasing the size of the response. I've got curves here for the X, C and L bands, and as we move down, we're increasing the wavelength. So as you can see, for a particular size of corner reflector, as we increase the wavelength, we're reducing the equivalent radar cross-section for that corner reflector. This gave us a bit of a problem since we wanted to use our corner reflectors for all of the different flavors of SAR, so X, C and L band. And we realized we would probably need to compromise on the size of reflector we use to be able to use all these different types of SAR. So we did some experiments to find the best size of corner reflector that would work for these different frequencies. Our primary use was for deformation monitoring, as I've discussed, but an important secondary consideration was to use these corner reflectors for calibration and validation of the orbiting SAR satellites as well. So we manufactured prototype reflectors with 4 different sizes to find the best compromise size. We also experimented with different surface finishes of these corner reflectors, and we manufactured 3 of each design so that we could test the manufacturing consistency of these corner reflectors. So in total we had 18 prototypes to experiment with. Our first experiment was conducted at the Defence Science and Technology Agency. They have an outdoor radar test range at Adelaide. And what we did was we mounted the corner reflectors on a turntable in the centre of this, in this radar reflection range. And as we rotated that turntable and rotated the reflector, we shone a radar on that reflector and measured the radar cross-section for that reflector. So we performed the experiments at X and C band and on the 1 metre and 1.5 metre corner reflectors. It was quite a difficult experiment to set up given the size of the corner reflectors, and we needed to use cranes to come in and lift the corner reflectors onto the stand at the end of each test. We also were very careful to make sure that the corner reflectors were precisely aligned with respect to the radar, so we used digital levels and plumb lines to make sure that the reflectors were perfectly facing the radar itself. So here's an example of the response that we see from one of these corner reflectors. On the x-axis we're looking at the azimuth of rotation through the corner as we rotate the turntable. A 0 azimuth corresponds to the time when the reflector is perfectly facing the radar. And on the y-axis we're looking at the RCS, the radar cross-section. And as you can see, the peak radar cross-section is occurring as we're facing the corner reflector directly onto the radar beam. But then you get this symmetrical pattern with spikes as you rotate that away. And these are often called Batman plots, and perhaps you can see a resemblance to the Caped Crusader there. If we aggregate all the results for all the corner reflectors and extract the peak radar cross-section, that's what I'm plotting here on this graph. So what I'm plotting on the x-axis is the results for each of the corner reflectors from 1 to 12. And then what I'm plotting here is the difference between the measured peak radar cross-section and the theoretical value that we calculate from the equation I showed you earlier. The red points are the results for C-band. And as you can see, for these corner reflectors here, which are 1.5 meters in size, there's a pretty good consistency amongst those measurements. And those corner reflectors are consistently about 2 decibels less than the theoretical values. The blue points are the results for X-band, and the consistency is not quite as good. Nevertheless, we know now the absolute radar cross-section for all these corner reflectors, and that's important if we want to use these corner reflectors for absolute calibration and validation of the radar satellites. Our second experiment was to deploy these corner reflectors out in the field and measure them with real SAR imagery from orbiting satellites. So between December 2013 and May 2014, we deployed all 18 corner reflectors on a grazing property in Gunning, which is about an hour's north of Canberra on the Hume Highway. And these are some photos of each of the reflector sizes deployed at Gunning. So you can see the smallest one is no bigger than a ute, but the bigger one is much bigger than a typical ute. So there were some challenges in handling some of these bigger corner reflectors themselves. So we imaged the corner reflectors with all the available radar imagery at the time of the experiment. So there was 3 commercially available satellites. There was RadarSat-2, which uses a C-band SAR, TerraSAR-X, which uses an X-band SAR, and Cosmos SkyMed, which also uses an X-band SAR. We also had some imagery from the Indian RISAT-1 mission, but I won't talk about that one particularly today. If we look at the response of the corner reflectors in the TerraSAR-X imagery, this is what we see in the amplitude image. So we have 4 corner reflectors in the image here, as shown by where the laser pointer is pointing. And we have a size progression of these different sites. So this is the smallest corner reflector, 1 metre in size, 1.5 metre, 2 metres and 2.5 metres. So what you can see is a general increase in the magnitude of the response of these corner reflectors in the image. What you may also see is that the response itself is cross-shaped. And this is a function of the limited bandwidth of the SAR that is used, and the processing that's used to focus this image was use a Fourier transform and a match filter. But it gives this characteristic impulse response function for each corner reflector. If we compare that now to the Cosmos SkyMed image, you can see a similar thing. And it's a pretty similar image to TerraSAR-X, given that they're the same wavelength and very similar spatial resolutions of the imagery. Though if we compare that to the C-band image, you can see that the spatial resolution of the C-band image is not as good, but nevertheless we do still see the size progression of the corner reflectors as we increase the size. So what we wanted to do was measure all the corner reflectors in all the images and extract this quantity, the signal to clutter ratio, which is essentially the signal to noise ratio. So what we did was to draw a cross around this impulse response function for each corner reflector, add up all the amplitude values within the cross to give us our total energy for the corner reflector. We then calculated the average background values of backscatter around the corner reflector, so we added up all the values within these 4 square regions to give us what we call the clutter for each site. We then compute the signal to clutter ratio using the total energy divided by the clutter. And then we can convert that value to an expected height error or phase error using empirical relationships. So for an X-band corner reflector that's as bright as 25, has a signal to clutter ratio of 25, that will give us an equivalent height error of about 0.1 millimetres. So first I wanted to show you the temporal changes in clutter that we observed during the gunning experiment. The different colours are showing the results for the different radar imagery, and each point shows the response for each corner reflector. Now I don't expect you to see anything through all this spaghetti, but the important thing here is the trends that we see. In particular, between the beginning of the experiment in November and February, there's a general decline in the magnitude of the clutter intensity. And this is because the summer was very dry that year, and the amount of vegetation that we saw at gunning was gradually dying off, and there wasn't any rainfall. In February, though, there was about 60 millimetres of rainfall over a course of 2 or 3 days, and this changed the character of the clutter. So we can see that the clutter is then increasing since the rainfall occurred. So this SAR imagery can be used to make some inferences about maybe soil moisture changes that are occurring through time. And it also impacts on our phase error estimates using the signal to clutter ratio. So now what I'm showing you is the height error results for all the corner reflectors and all the data through time. So again, the x-axis is time. And then what we're showing here is the line of sight equivalent height error. Again, don't worry too much about the detail, but the main result of the experiment was that we found that at C-band, so for the RadarSat-2 and the RISAT-1 imagery, the 1.5 metre corner reflectors gave us a height error of less than 0.5 millimetres, whereas at X-band we got a height error of less than 0.1 millimetres. Now, given that we're looking for a very small error component just due to the corner reflector itself, this seemed like reasonable values for our target deformation, given that we have other sources of noise in the interferograms like I showed you earlier. Then we saw this interesting departure from the general trend for this one corner reflector, and when Mark went out to investigate what was happening here, we found that the corner reflector was flooded. Now, our corner reflector design had a hole in the corner of the reflector there, which is designed to drain out rainwater as it accumulates, but this corner reflector had been a popular roosting spot for birds, and one thing leads to another. That blocks the hole, and we ended up with a flood in the corner reflector. So I'm highlighting this just because we learned a lot of lessons during this prototyping, and we actually modified our design to include many more holes and make it much harder for that much guano to appear in the corner reflector to flood the corner reflectors. So the experiment in the end, we found that the 1.5 metre corner reflector was a suitable compromise design for both of our targets, which was deformation monitoring and calibration and validation. And although we didn't have L-band imagery to test the corner reflectors at the time, we could estimate that the height error for this size reflector would be around the 10 millimetre value. So finally, I'll just talk about the construction of the geodetic network in the Surat Basin, and that's what's shown in this map, as I showed you earlier. A reminder that we constructed 65 new sites, and at each of those 65 sites has a new geodetic survey mark for doing campaign GNSS surveys, and our colleagues in Queensland are currently undertaking the first of these campaign GNSS network surveys at this time. The yellow points show the subset of marks where we deployed corner reflectors, and there's 40 of those sites. So the first, probably the most difficult part of the project was to find suitable sites to deploy this infrastructure. And when you go to this region of Queensland, you find a lot of this sort of activity ongoing. Anything that's fixed to the ground may have pock marks from bullets and target practice that's ongoing. And given that this sort of stuff is rife in the area, we wanted to make sure our sites were secure and that the infrastructure would be long-lasting. So the idea was that we would find private properties to deploy this infrastructure. And our team did a very good job of finding 38 sites on private property to deploy this infrastructure. But given that the gas companies have already been through this region and installed well infrastructure, there's a lot of resistance from landholders to installing additional stuff on their properties, and this sort of thing is quite noticeable as you drive around the Surat Basin, signs from the Lock the Gate initiative and that sort of thing. So there was significant issues in getting access to these sites. So the remaining sites, 27 sites, were installed on road reserves that we found in Queensland themselves. A second part to this reconnaissance was that we undertook full cultural heritage clearance for these sites. We employed the services of elders of the various indigenous groups in the area to ensure that these sites weren't going to affect the traditional uses of the land. So we were very careful to make sure that these things were fully compliant in that way. So here's the survey mark design. All of these marks are installed into the soil in the sedimentary basin, and that soil is black soil, which can exhibit large swelling signals as it moistens and contracts. So we wanted to isolate our geodetic marks from this potential effect. So our survey mark penetrates to a depth of 6 meters or more, and the mark itself is surrounded by a concrete column, which is designed to isolate it from the swelling of the soils in the near surface. And at the surface itself, the actual ground mark looks like this. We can cover it over with a valve box lid, and it's actually pretty invisible to anyone on the surface. So the construction was won by tender by a mob called MIPEC based out of Gladstone, and they operated in 3 teams to pass through the network and install this infrastructure. And I'll just talk you through the process of that construction. So each hole was drilled to a depth of about 6 meters with a 450 diameter drill bit. That hole was then sleeved with a PVC sleeve, and a reinforcement cage was inserted into the hole. We then drove the geodetic mark into the ground beneath that hole until it met suitable resistance. And we made sure that the rod was aligned vertically during this process using a custom jig installation. We then poured concrete into the hole using a tremie and a vibrator to make sure that the concrete had suitable strength and integrity throughout its whole depth. And after the concrete had cured, we levelled off the land to repatriate it at ground level and installed the access valve box lid here. And we did post-construction alignment checks to ensure that these things were suitably vertical for geodetic surveys. The corner reflector had a slightly different design. The corner reflectors were installed at 40 sites within about a distance of 30 metres of the co-located survey mark. They had their own infrastructure as a result, so they were installed on a concrete slab, and that slab was floating above the ground surface and supported on 4 concrete columns. Again, this design was to try and isolate that concrete slab from the soil swelling signals at the surface. I've already mentioned that we used a 1.5 metre corner reflector. So the construction process involved drilling the 4 holes, sleeving those with the PVC pipe, and then pouring the slab itself on top of decomposable formwork. And after some time, this decomposable formwork will rot away to leave the air void underneath to separate the slab from the surface influence. We boarded up this subslab void to hopefully remove the temptation for animals to make this their home. And then, hey presto, there's what the finished corner reflector would look like. We measured the positions of all this infrastructure using RTK surveys. So as demonstrated by Shane and Anna here, the mark for the corner reflector itself is based underneath the corner reflector. So we measured the geodetic position of the corner reflector and then precisely align each corner reflector for the orbiting SAR satellites that it will be imaged by. We also redeployed the 6 larger corner reflectors from the prototyping exercise, and the reason we did that is because they're highly desired by the Japanese for calibration of their new L-band SAR mission, given that the size of them is suitable for the longer wavelength of that mission. So those have been used over the last half a year for calibration and validation of that mission. These had their own challenges. We had to use a 3-man team and a truck-mounted high-up to actually assemble these corner reflectors, given the considerable weight of these panels. Several of the sites are located near to coal seam gas infrastructure. In fact, this site is probably only a few hundred metres from one of these extraction sites, and as a result, we may see some interesting signals going forward observed by the geodetic infrastructure. We had a lot of interest from local stakeholders. Camels, sheep, cattle, and even emus came and are interested in what's going on here. On the private property sites, we tended to fence the corner reflector so that the roaming cattle wouldn't interfere with the corner reflector and use it as scratching posts and potentially injure themselves. In the case of road reserve sites, we didn't actually use a fence, and who knows, maybe we'll go back and these emus will be making a big nest in there and blocking the signal, but time will tell. So the construction was completed in late November last year, and I think our team was pretty keen to get back to Canberra, needless to say. So since November, we've been imaging the corner reflector with a number of SAR missions. Since gunning, there's been some new launches of missions, such as the Sentinel-1 C-band mission and the ALOS-2 L-band mission, which I just mentioned. We bought some imagery for TerraSAR-X and RadarSat-2, and what we're finding is that the X-band imagery, the signal-to-clutter ratio is coming out at about 50 decibels, RadarSat-2 at about 36 decibels, Sentinel-1 at about 32 decibels, and ALOS-2 at about 30 decibels. And these signal-to-clutter ratios are pretty good. They're much higher than we were expecting, and this results in better than expected height errors for this corner reflector infrastructure. So this infrastructure will be more and more useful as time goes on and as images are more routinely acquired. And I just wanted to mention finally about the new Sentinel-1 mission, which is a pretty exciting mission for the work that we do. It's a new C-band mission. There's going to be 2 C-band satellites working in tandem. The first was launched in 2014, and that will give us a minimum revisit of about 6 days, so potentially an image every 6 days over different regions. Importantly, the mission policy is for open access to the data, which has never been possible for a SAR image before. And in Australia, there's been a commitment at this time for 5 images per year over the full Australian landmass, so that's quite exciting. But we've actually sold the corner reflector infrastructure that we've deployed as a calibration validation tool to the Europeans, and they've been evaluating that infrastructure for ongoing cal-val of that sensor, and that's great for us because it means that there'll be a lot more images than 5 per year acquired over the Surat Basin. So this is very, very good news for ongoing monitoring of this region. And we've had a quick look at Sentinel-1 data over the Surat Basin region. This is an interferogram generated from images 48 days apart. And the fact that you can see fringes here implies that there's very good coherence. So if we can get 12-day revisit, the coherence will be even better. So it's great news for the future and monitoring this region. So I'll leave you now with a summary. Synthetic aperture radar has many applications in the geosciences, and one in particular is a geodetic technique called InSAR, which we can use to map spatial and temporal patterns of surface deformation. I've talked to you about the design of corner reflectors, which we've been using for multi-frequency InSAR analysis and for calibration and validation activities. And I talked to you about the construction of a new geodetic network that we've deployed in Queensland to help with future geodetic monitoring in this region. And if you're interested in any more information on this work, we recently released 2 publications. There's a paper in the Australian Journal of Earth Science that describes the geodetic network in much more detail. And we also released a GA record earlier this year that goes into quite a lot more detail on the corner reflector experiments that we were doing. So thanks for your attention.